Okay, in this video, we're going to be starting assignment number 11 from my Calc CD multivariable class. It's going to be about the fundamental theorem for conservative vector fields. So let's take a look at what that says. So if the field f is the gradient of a function f on the domain D, then these will be true. So if R is a path along a curve C from the point P to the point Q in domain D, then the line integral f dot dr is just going to be f of q minus f of p. So it's going to be f of where you end minus f of where you start, which is almost exactly the same as the fundamental theorem of calculus from like Calc 1. And then there's another fun fact about this, which kind of makes sense. If C is a closed curve, meaning that P and Q are the same point, so you just go around that curve and you end exactly where you start, then you have a slightly different notation to show that it's a closed curve, but f dot dr is going to be equal to 0. But remember, we already said that our vector field f is the gradient of f, so of our scalar function f. So let's do a problem, see how it works. If f, our potential function, is xy sine of yz, and f, our field, is the gradient of f, our potential function, then we want to find the line integral f dot dr, where c is any path from 0, 0, 0 to 1, 1 pi. All right, so our line integral in this case is just going to be f of where we end up, which is 1, 1 pi, minus f of where we start, which is 0, 0, 0. And if we start calculating that, we will get 1 times the sine of pi by plugging in 1, 1 pi, and then minus 0 times 0 sine of 0. And overall, this just gives us the sine of pi, which is 0. Now, what if we did this the other way, right? The longer way, I guess, the way that we previously were doing these. So we would have to calculate r. And so I'm just going to kind of blow through this. R is going to be x is t, y is t, and then z is pi times t. Remember, we're going 0, 0, 0 to 1, 1 pi. And then that'll be from 0 to 1 for t values. Now I would need to calculate the gradient, right? I need to find our vector field. So that's partial x, partial y, partial z. And then I would want to do the integral from 0 to 1 of, we're going to do the composition, right? So it's like f of r of t, and dot that with r prime. So that's what this is going to look like. And I used a calculator on it, and I got 0. Same answer. The key thing here is that this is way better, right? So if f is actually the gradient of our function, so lowercase f is the potential function, f, our vector field, is the gradient of that potential function, we can use the fundamental theorem of calculus, of vector calculus on these. So that'll be it for this one. I'm going to come back, do a ton of problems, so I'll see you in the next one.